Hello everyone, my name is Christine Dewi from Chaoyang University of Technology, Taichung, Taiwan. Today, I want to present my research title, The Study of Robust Detection Method for Improving Traffic Sign Recognition Based on Spatial Pyramid Pooling. This is my outline today. Chapter 1, Introduction. Chapter 2, Literature Review. Chapter 3, Traffic Sign Recognition with Various Analyses. Chapter 4, Robust Detection Method for Improving Small Traffic Sign Recognition based on SPP. Chapter 5, Conclusions and Future Works. Traffic sign recognition systems are crucial in numerous applications in the real world, such as autonomous driving, traffic surveillance, driver assistance, road network sustenance, and investigation of traffic disturbance. As all we know that the SRS contributes beneficial information for smart vehicles, including direction and alerts for advanced driver assistance system and cooperative intelligent transport system. Small traffic sign is difficult to identify accurately. Why? Because developing a robust TSR in real time represents a difficult task given the latency during the test time and the need to identify a small target. Our objective is how to detect the identify traffic sign in real time and represent a difficult task given the latency during the test time and the need to identify a small target in advance. These research dissertations review and assess different state-of-the-art object detectors, primarily thus intend to improve small traffic sign detection and recognition. This is my dissertation flowchart. As all we know that in the computer vision, especially for object detection and recognition states, it will be divided by two steps or two states. The first one is the model training states, and the second one is the object detection and recognition states. So we start from load the data set, and then I'm doing the anchor box setting calculations. Also, we'll do the parameter setting for scale analysis, and then the network initialization. And of course, the model training using the SUM model include ResNet 50, Densenet, Tiny YOLO V3, and YOLO V3. And of course, combined with the spatial pyramid pooling. I'm training until the loss converts. After that, we will get the weight analysis. Okay, we will get the substance of weight, and we will use this weight in the second stage for the object detection and recognition states. Of course, we will start from input the image and we load the weight, the result from the training states. After that, we will do the prediction. And we calculate using the non-maximum separation. We will choose the highest confidence. After that, we will show the detection and recognition result. Okay, and in the each step, it produced the some paper during my research. CNN was recently implemented for object recognition and detection, and the recent deep learning algorithms, specifically those with CNN, and in here I'm choosing the YOLO V3, have shown great power in high precision target detection project. That is why in this research I'm focused on the YOLO V3. YOLO encapsulates computation in a single full CNN rather than providing a series of region proposals. And YOLO V3, as all we know, it's using darknet 53 as the backbone network to replace the darknet 19 and use multi-scale estimation. We can see in figure 2, this is the SPP layer in network structure. And there are several advantages of SPP. First one, SPP provides a fixed length result, and the input image can be of all sizes. SPP operates multi-scale space while the pulling of sliding windows use just one window. SPP allows us to produce images of arbitrary size for testing and enables us to supply images of varying dimension and size during the training process. For the YOLO V3, it consists of 107 layers with deep characteristics and was built on darknet 53, as we can see in figure 3. YOLO V3 has demonstrated better than ResNet 101, 152, or darknet 19. The other method is tiny YOLO V3. It is the YOLO V3 with a reduction in the convolutional base layer is another version named tiny YOLO V3. The running speed of the tiny YOLO V3 is significantly faster than the previous variant of the YOLO, but the detection accuracy has decreased. So it has the plus and minus. The backbone network of tiny YOLO V3 has only 7 convolutional layers and 6 pooling layers. For ResNet 50, it contains of 34 to 152 layers and characterized by a very deep network. The residual network architecture uses the residual learning method in its components. The deeper layers of ResNet can be trained quicker than the earlier ones, and this model applies the batch normalization method for avoiding overfitting. Both of the features extractor are built with 4 residual blocks and the first 3 layers. Okay. And the box classifier features are gained by the last layer of the 4th residual block. Another method is Densenet, and Densenet mainly consists of a dense block, a transition layer, and a rate of growth. So we use 4 dense blocks in our Densenet architecture to detect the traffic sign. We also choose some model assessment to evaluate our method. We use the precision and recall, F1, MAP, IOU, and loss value. The next, we want to discuss about traffic sign recognition with various analyses. The first analysis, we focus on the anchor box. Okay, convolutional with anchor box. We can see in figure 7, the bounding box prediction. It is the predicted box in the blue color and prior box in the black dot. Px, Py, Pw, Ph are the x and y core coordinates, width and height of our estimation, and the network outputs is the Tx, Ty, Tw, and Th. The grid's top left coordinates are Cx and Cy, while the Pw and Ph are the anchor dimension for the box. So we use this setting calculation for our anchor box. Considering there is no data set for Taiwan traffic sign yet, we have to create a database and compile the image for ourselves. And in this experiments, for focus on the anchor box analysis, we use 400 images for each class. And in this work, we only focus on the stop sign, okay? To analyze the benefit of anchor box, we just focus on the stop sign. You can see this one is the usual stop sign. This is the Taiwan stop sign. We also define our experiment setting as 3 experiments, experiment 1, 2, and 3. And what is the difference between each experiment is the anchor calculation. In the experiment 1 and 2, we use the original anchor setting from COCO dataset. The experiment 1, it has 80 class and the filter is 255. The sign just stop sign. The experiment 2, it still use the setting for anchor box calculation using the COCO dataset, but we define our class. So I have two classes. The filter is 21. This one is for stop sign and Taiwan stop sign. In the experiment 3, we calculate our anchor based on k-means. And the class is 2, filter is 21, using stop sign and Taiwan stop sign. We generate the anchor calculation based on k-means calculation. So it will produce the new anchor setting. This is the preview result of each experiment in experiment 1, experiment 2, and experiment 3. As we can see in here, experiment 3 gets the highest accuracy and can detect multiple images compared to other experiments. This is another result. This one is for experiment 2 and experiment 3. And in here, still experiment 3 in image P got the highest accuracy. So based on the anchor box analysis, we can summarize that the trend of accuracy increase and the time is decreased from experiment 1, experiment 2, and experiment 3. The best experiment setting is experiment 3 because it can improve the performance accuracy and the time is faster than others. For experiment 3, it can detect the sign precisely compared to other experiments. Then the anchor recalculation based on our data set is very important and it is proven in our experiment. Determine our anchors correctly is very important so that our neural network will understand that small, large, or extraordinary objects exist according to our data set. The next analysis, we focus on the scale analysis. So deep learning for traffic sign recognition based on SPP with scale analysis. In this experiment, I have 6 experiments set up with various scale in detail. So in the YOLO configuration file, it has the scales and we can change the scale. And in these experiments, I want to know what is the effect of that scale. In the scale configuration, I'm using the 0.1, 0.1, and 0.2, 0.2, 0.3, 0.3. So, and the model, of course, for YOLO F3 and YOLO F3 SPP with different scales. Okay, so in total, we have a 6 model. And then I'm developed our Taiwan prohibitory signs that contains of P1, P2, P3, and P4. This one is for no entry, no stopping, no parking, and speed limit with the total image of each class, as we can see in table 5. So after doing the experiments, the summary for scale analysis is the highest accuracy is obtained when using the original scale 0.1, 0.1. The faster detection times are indicated when using scale 0.3, 0.3. The precision declines compared with the initial YOLO F3 scale. The precision of YOLO F3 SPP improved with various size. Finally, the MAP analysis of all YOLO F3 SPP versions outperform YOLO F3, and the result of the MAP suggests that the YOLO F3 SPP model fits well on different scales than YOLO F3. The next analysis will focus on weight analysis. Okay, so far we already discussed about anchor analysis, scale analysis, and now weight analysis for various prohibitory sign detection and recognition using deep learning. As all we know that in the darknet will provide 3 weights: the best weight, the final weight, and the last weight. And what is the difference between these weights? We will do in this experiment. The evaluation of specific models include measurement of average mean precision MAP, workspace size, detection time, intersection over union, and the number of billion of floating points operations, or PFLOPs. So this is the experimental model setup. The best weight, final weight, and last weight for each YOLO V3 and YOLO V3 SPP, and we name all the model YOLO A, B, C, D, E, F. So it will make easier to understand what is the weight that used in that experiment. Okay. After doing the experiment, we can summarize that SPP was employed to fit image with the weight analysis provided by .NET 53 during training and implemented in the YOLO V3 config file. The result reveals that the SPP can enhance the performance of identifying the Taiwan prohibitory signs. The MAP result explained that YOLO V3 SPP model gives the best performance compared to YOLO V3. The best weight will give the highest accuracy. The last weight and final weight obtain the similar accuracy, and the fastest detection time is the last weight. Next, we do the evaluation of robust spatial pyramid polling based on convolutional neural network for traffic sign recognition system. And in this experiment, we introduced the brief survey on CNN algorithms for object detection, especially for YOLO V3 SPP, YOLO V3 Densenet, Densenet SPP, ResNet 50, ResNet 50 SPP, Tiny YOLO V3, and Tiny YOLO V3 SPP. So we will combine all algorithms with SPP. The examination determined that YOLO V3 SPP discovers the best accuracy, and SPP enhanced the performance of all models. So this is the some result and discussion. As we can see in here, this picture is for the YOLO V3 and YOLO V3 SPP. YOLO V3 SPP can detect the multiple object, multiple sign. Whether YOLO V3 just can detect the one sign. This one is Densenet and Densenet SPP, ResNet and ResNet SPP. Next is Tiny YOLO V3 and Tiny YOLO V3 SPP. Summary, in the experiments, the MAP measurements result reveals that YOLO V3 SPP outperforms other model. YOLO V3 SPP obtains the best total PFLOPs 65.69 and MAP 98.88%. SPP can enhance the total PFLOPs 0.378 from 65.312 to 65.69. That is why making YOLO V3 SPP powerful to recognize the sign. The experiment result reveals that SPP improves the effectiveness of identification of Taiwan's prohibitory signs, and SPP develops the achievement backbone network of YOLO V3, ResNet 50, Densenet, and Tiny YOLO V3. The next chapter, we focus on robust detection method for improving small traffic sign recognition system based on SPP. In this work, we apply an image data preprocessing and color-based detection step, including mask, blur, binary, close, error, and delay that could be seen on figure 26. So we implement the color-based detection method. As we can see in here, this one is the process of mask red, and then mask red and blur binary, close error, and delayed. Our proposed method contains of 2 steps, including color-based detection and recognition state using YOLO-V3 SPP architecture and shown in figure 27 and 28 respectively. As we can see in here, we have the original image, and we will do the data preprocessing for the color-based detection. And the step is include for mask red and blue, blur, binary, close error, and delay. After that, we know exactly where is the position of our sign, and we do the feature extraction. We will use the feature extraction in the next step. In the next step, the input image from feature extraction, this one, we use, and then in our SPP, this one is the spatial pyramid polling. We'll do the calculation, do the pointing box and class prediction, and of course, we'll show the detection and recognition result in the original image, and it will show the time, prediction time, and the size and the accuracy for each sign. For the data set, we use the Bayesian traffic sign dataset to evaluate the proposed method. We can see the PTSD dataset in the figure 29. Its image is 1,628 times 1,236 with the total of 9,007 images in the dataset and 62 class. This is the PTSD dataset statistics. It's divided by the area small, medium, and large. The total of each category we can see in table 18. Okay, for S, M, and L. And the training result, training performance on the PTSD dataset we can see in here. So I'm using the YOLO-V3 SPP, Densenet, and Densenet SPP. As we can see in here, the YOLO-V3 SPP achieved the highest performance, 99.28% for NAP. And for the discussion, we use 771 randomized images to form the PTSD dataset for examination with different size, S, M, and L. And the analysis of precision and time of the experiments are shown in figure 33. So we can see in here, this is the testing accuracy using the PTSD dataset with various size target. YOLO-V3, V3 SPP, Densenet, Densenet SPP for each category, small, medium, and large. And this is the average of each category. As we can see in here, YOLO-V3 SPP achieved the highest accuracy for average accuracy in compared to other algorithm. And in the small category, it also achieved the highest performance for each category. In table 20, it shows the comparison of detection accuracy for our approach and previous research for small, medium, and large target. Okay, so based on the previous research for T. Yang et al., using the faster RCNN and attention network and FRPN, using the same data set, and then we follow the setting of small, medium, and large for each data set. And the last one is for our method, color detection plus YOLO-V3 SPP in the same PTSD. We can see in here that we can improve the performance result from the previous result. This is some of the PTSD recognition result we can see in this figure for each YOLO-V3, YOLO-V3 SPP, Densenet, and Densenet SPP. How about the PF-LOPS workspace size and layers comparison? We also calculate for the, we doing the analysis of its PF-LOP workspace size and layer comparison. In here, we can see that YOLO Phase3 only have 107 layers. YOLO Phase3 SPP 113 layers. Densenet load a big layer, 306 layers. And Densenet SPP 312 layers. And for the workspace size, of course, Densenet is bigger than YOLO Phase3. For the PF-LOPS for YOLO Phase3 SPP is the highest among others algorithms. That is why it can achieve the highest performance between other algorithms. This is our conclusion and future works. In this dissertation, a robust detection method to improve the recognition of small traffic signs based on spatial pyramid polling integration has been proposed. The analysis of the introduction of traffic sign with adjusted anchors is discussed in details, and the experiment and discussion were conducted on deep learning TSR based on SPP with scale and weight analysis. In the detection stage, we employ a color-based detection method to detect the sign in the image with various target types. Besides, we perform a detailed series of experiments to validate YOLO Phase3 SPP efficiency in defining different target size. We have improved the performance of detecting small traffic signs in the previous research on the PTSD dataset. Our results have shown that YOLO Phase3 SPP obtains the highest total PF-LOPS. In future research, we will explore YOLO Phase4 optimal speed and accuracy of object detection to achieve better performance and result. Future studies will combine YOLO V4 with color-based detection and explainable AI. Also, we'll focus on the real-time detection by video. Thank you and see you in the next video. Bye-bye.